Hello, this is section 5.1 for Calc AB, and today we're going to be talking about slope fields, and we'll revisit the topic of differential equations that we did in section 3.7. So there's also Euler's method in this section that we don't cover. That's not part of the AB curriculum, but if you'd like to know about it, come see me. I'll explain it to you. It's interesting. So a function y equals f of x is called a solution of a differential equation if the equation is satisfied when y and its derivatives are replaced by f of x and its derivatives. So basically, you're given a differential equation, which can look a couple of different ways. You might say, Cogswell, it's not dy equals f of x times dx. And I agree. A differential equation can also just be an equation that has derivatives in it. So, and basically you're given a function, and we're going to see, is this a solution to this differential equation? So, and as you can see, you need the double derivative and the original function. So that's what we've done. We found the double derivative. That's here. And when you plug this into the equation, added to the original function, which was cosine of x. So we're just plugging the double derivative and the function in. And sure enough, yeah, it does equal 0. This is a solution to the differential equation. But when you try it with e to the negative x, again, we found the double derivative, then did the double derivative plus our original function, but that does not equal 0. So this is not a solution to the differential equation. And then one more time, c plus sine of x. When you found the double derivative, did the double derivative plus the original, oh, it does actually work. So a and c, they look different, but they are both solutions to this differential equation. Okay. Now, if ever you want to, now notice you had that c value, so particular solutions of a differential equation are obtained from initial conditions, just like what we were used to. If ever we wanted to find the c value when we did the antiderivative, they would give you an initial point or some type of point on the curve so you could find the c value. Okay. So for the differential equation here, so notice it's an equation with a derivative in it, verify that this function is a solution to this differential. So that's what we did first. We need the derivative, so I found the derivative here. Remember, e is exactly the same thing times the derivative of the exponent. And I plugged our derivative in, plus 2x times our original function, which was here. So that's what's going on. And that does actually equal 0. So this is me verifying that, yes, this is a solution to the differential. Then it wants us to find the particular solution, and notice they give you an ordered pair, so you can easily plug that ordered pair into your function, solve for c, and there's your particular solution. All right? Okay, I found this paragraph on a worksheet. So slope fields provide an excellent way to visualize a family of solutions of differential equations, and we saw this up here. We had two completely different functions that were a solution to this differential equation. So these differential equations have a family of solutions. It's a good way to think about it. Some differential equations can be solved algebraically, the ones we just looked at, and the slope field for these differential equations can be used to verify that the algebraic solution matches the graphical solution, which I'll explain. I know this is a little confusing at first, but the key thing is other differential equations cannot be solved algebraically, and the slope fields for these differential equations provide a way to solve the differential equation graphically. Okay. So suppose f of x is a known function, and we're interested in finding a function capital F of x. Notice we're going backwards, such that the capital F of x satisfies the equation, your differential equation. If we interpret dy dx as the slope of the tangent line to capital F of x at any point, we can obtain the geometric description of capital F of x by choosing a rectangular grid, calculating the slopes of tangent lines at numerous grid points, and drawing very small segments with the correct slope at each grid point. These line segments show the direction of the graph of the original function. Okay. So here's what that means. Here's what a slope field looks like. So notice we're starting with a differential equation. So I also wrote it as y prime equals x. So what you're doing, you're following these three steps. We have our rectangular grid on the xy plane. Now we're going to calculate the slopes of the tangent lines at numerous grid points. So if you plug in 0, 1 into here, so there is no y value, so it's just 0. Yeah. But if you plug in 1, 1, well, x value is 1, so that's my slope of 1 right there. If you plug in negative 1, 1, There's -1. So I'm plugging in these different points. So -2, 0, well, that would be -2. So I tried to make it a little bit steeper. And then -3, 0 would be even steeper negative. And over here, this would be a +1 slope, +2, +3. The AP exam, they have said that the most important thing is to make sure that it's slanted correctly. So if it's a positive slope, it needs to be positive and vice versa, or 0 slope. Okay. And then, so after you've plotted, these are our little mini tangent lines. These represent the slopes of the tangent lines at these data points that we've plugged into our derivative here. So that's where I'm getting all these slopes from. But now you kind of get an idea. If we want to go through -2, 2, I plotted that point, you can use those tangent lines to help guide you on how to sketch the curve. So it's kind of looking like it's a nice little parabola there. Right? So find a possible formula for y. So you can see that it's a parabola by just letting the little tick marks guide you. But this is one that you can actually solve. So move the dx over, do the integral of both sides, and there it is. There's our parabola. Okay. But the problem is there are some differential equations that you can't solve, and you need the visual to see what's going on. All right. And this is an excellent real life problem, because things aren't going to work exactly. They're not going to follow an equation in the real life. So it's good to be able to see what's going to happen and let it guide you, because there's not going to be a perfect formula that fits your scenario. Okay, so we solved it by hand. We tried to sketch it and then find the equation, and then we were given that ordered pair to find that C value. So we were able to actually write the equation of what we tried to sketch using the tick marks, using the slope. This is a slope field, using the slope field. Okay. All right, so draw the slope field. So how I usually like to do this, so of course get your rectangular grid. I start with the axes, so I always go along. So this would be when x, obviously your y values are 0, so x is -1, or -1 here, -2, 1, 2. And then I kind of made a table. If you think a table will help you, go for it. And then I just work on each quadrant. So plug in 1, 1. As you can see, if you plug in 1, 1, you'll get -1. So that's what I tried to do, a little tick mark that has a slope of -1. And hopefully you kind of get the idea. So can you kind of see that this graph is probably going to be something like this, right? And it's just tedious, but you'll be okay. All right, now going backwards. So what we just did here was we sketched some slope fields. Now we're going to try to read the slope fields. And if you're a perfectionist like me, these can be a little bit frustrating to work with. So if you're trying to work backwards, look for slopes, places where the slopes are 0. Look at the slopes along the x and y axis. Look to see if the slopes only depend on x or y. So look vertically or horizontally. If you notice back up here, when my differential was just in terms of x, all the slopes vertically are going to be exactly the same. See that? So that's a good rule of thumb to always check. That's one of the first things I check, steps 4 and 5. And then look to see where the slopes are positive and negative. That's kind of if you haven't figured it out by now, that's kind of your last ditch effort to figure out what's going on. All right, so here's a good example. Match the differential equation with its slope field. All right, so automatically I'm looking to see, is anything the same vertically or horizontally? And this one definitely the same vertically. So that means it depends on x. So that's going to have to be here, B. So these are linked. Okay. So now when I'm looking at these two, I'm immediately looking to see, well, do we have any slopes that are 0? And it's looking like at 1, 1, you have a slope of 0. So that's kind of looking like A might be a good contender. Also, I notice, look for ordered pairs that you can easily identify. So at 0, 1, that's a negative slope. So that would be a good way to check yourself. If you're thinking A is probably 3, well, if you get a negative slope, if you were to plug in 0, 1, are you going to get a negative number? Okay. Okay, so I'm pretty sure there's a mistake right here in the notes. This should be x minus y, because you can see right there at 0, 1, that is definitely not a negative slope. So I went on here, and I don't know if you can see this or not. Let's come over here. So I actually sketched, I had it, this is a Desmos. It can do the slope fields for you, and you can see, yeah, it's definitely, okay. So sorry about that, just a little mistake in the notes there. So, all right, let's see if we can go back to the notes. Okay, but that is a cool little feature in Desmos. You can actually you can have it graph your slope fields for you. Okay, just go to Google, type in graphing slope fields, and Desmos will pop up and go in there, and you can kind of play around with it. Okay, all right, and then here, number 2, so find where your slopes are 0, and then you can kind of easily see that it's definitely some type of periodic function. But that's kind of we're able to rule out these other two. Okay, so all right, and then here's another one shown at the left or at the right is a slope field for which of the following differential equations does this one fit? So automatically, first thing I do is I look horizontal and vertically. Are they all the same? No. So that means anything that's dependent on one variable is out. So I can rule out A, B, and E right from the get-go. Okay, so you're down to these two options. And in this case, now I'm going to go searching for, is there anything I know? So I see here at 0, 2, I know that is a definite slope and it's positive. Okay, good to know. Are there any slopes that are 0? I'm just looking for ordered pairs. You have another one down here at 0, negative 2. But see which ones fit. Okay, and then you just have to rule them out. Okay. All right, and then the last one here was one where we sketched. So again, make a table if you need to. Use Desmos. We have had some AP exams in the past where students have had to actually sketch the slope field. So make sure you're slanting your slopes correctly, and so forth. And then from there, this is my most frustrating thing, and I think it's just because I'm such a perfectionist. But after you've sketched your slope field, then they want you to plot a point at 2, 1, and then try to sketch. So try to use the slopes of the tangent lines to help guide you. And remember, this sketch that you're making is the original function. These are little mini slopes of the tangent lines to help guide you to graphing your function. And that's where I get frustrated because I want it to be perfect. And you just have to be very flexible and just do the best you can. Okay, so slope fields, just make sure you practice them. Take advantage of that Desmos website to help you out. And just realize the importance is these are most useful when you've got differential equations that you cannot solve. If you tried to take the antiderivative of this, you wouldn't be able to solve it. So you're depending on what the slope field looks like to kind of make a sketch of what your function would fit with the data type deal. Okay, so it's a really cool application concept. All right, but please do your homework and let me know if you have any questions.